Thank you. You can hear me? Yeah, awesome. I can hear myself. One side note, if I speak too fast, please shout out slow down, something like that. Let's test this. Slow down. Repeat after me. Awesome. Thank you. Great. Let's start. Yeah, I'm going to talk about transceivers as well. I mean, this is a section and network reliability. So how do we get or guarantee that our transceivers are reliable? Well, we were wondering and we just came up with some ideas. What nowadays you can do on transceivers, which is part 2, after I start a little bit with the intro we did together, is a bit error rate tester. There exists these big devices where you can do it. But some transceivers also have this integrate, and this is a big advantage. I'm going to tell you why. And one factor that is important, that is number 4, we have black boxes, which will be in 2 or 3 months revealed about what it is, because it's a series of presentations. So we are going to compare distance, which means different fiber length that we are connecting to the transceivers, and temperature. Because temperature, you know, in your racks is always a problem. It's really making us our heads hurt. So I analyze temperature and I also analyze distance. So these are the correlation we are going to look. There will be a live demo. So I brought some devices, so you can also see after the presentation. We can also have a look if you're interested in something else or more. And yeah, let's talk about these transceivers. And yeah, the Coherent from the past presentation are also candidates for that. They have a DSP and an MCU that drives the DSP. And I was talking about bit error rate tester, BERT, where you can run it on the device. And for example, you can define that there's a bit string that is being transferred from the transceiver directly. So you don't need to have a network gear that is through IPAv3, for example, sending the data. No, you can tell the transceiver, you generate the data, and I want to receive the same data. And with some verification, what it should have received, you can verify it, which means forward error correction. Of course, we always have that. And optical signal to noise ratio is like a second value we want to look at, because usually you have these 2 point of views. Normally, as someone connecting and getting links ready for the customer wants to have certain bandwidth, right? So what you measure with a bit error rate tester is the bit error rate, and it's simple. You have your number of erroneous bits divided by the total number of bits. That is one point of view, but there's also the other point of view, and there's a correlation, but you have to look at those separately, because this is all about signal. dB and dBm, usually when you measure your signal with some of the smaller devices where you can do this, is your optical fiber cable good enough or not? You usually get power values, Tx power, Ix power, or nowadays also OSNR. What is OSNR? It is a relationship between the signals, the useful signals, and the noise. If you're here outside the construction site and it is too loud, you cannot listen to me, you cannot hear me. If I speak up louder, well, you can listen perfectly. So there's a certain relationship between signal and noise. We always have noise. Everywhere is noise, and but the relationship is important. And that is the signal to noise ratio, basically, which you can measure. And these 2 values can be executed with certain diagnostic capabilities on these transceivers. And yeah, that's one of our experiments. I just cut off the head of a FlexOptix. It looks like that. And special thanks to Cisco. It's a little bit difficult to see. There's a heatsink on this transceiver sitting on it. I had to cut off the head of this FlexOptix because we need more ways to cool them down if for a longer time we want to run these kind of diagnostics. And yeah, that's an example of an 800G transceiver. We tested many of these transceivers, a couple of series on which we were interested. I cannot show you all the results, but instead I can show you and will show you the most interesting ones. And of course, we also have a coherent one here in between. And that one is particularly interesting. And why that is, I'm going to tell you in the later slides, but let's get back to 100G transceiver. The ER was particularly interesting because we had this with customers that they buy a transceiver, they're excited, they connected. Not all of them. I know we have experts here, but we also have had customers who are new in the market, and you have to watch for attenuation. If you connect a cable drum, and I was in this situation where I wanted to connect a 2-meter fiber cable and then a 20-kilometer fiber cable, where there are differences, right? This transceiver is meant to be run on 40 kilometers. So if you take a 2-meter cable and connect it to a 40-kilometer transceiver, you are breaking the photodiode basically. So in order to avoid that, what you have to do is to attenuate it. And you can watch in our job our limits, dBm. Yeah, these are the power, Tx power, X power, the maximum. But there comes a new challenge. The problem is, if I want to compare all these cables, well, at some points I have to attenuate them. And so what I ended up doing in order to better compare somewhat, I added different kind of attenuation. And the three first, which are 11 dB attenuation, where these are the most comparable, but after that I had to lower down the attenuation because if I don't do that, well, I don't get any signal anymore. But as you can see in this diagram, yeah, it's a little bit messy because there's a lot of correlation. But I want to pinpoint out one effect that is quite interesting when you start measuring bit error rate. First of all, the red section is a section outside of the Ethernet specification. You can go up to 2.4, 10 to minus 4, but it's not a good link anymore, but it's still within this IEEE specification. So that's something that works, but I mean, yeah, you want to have as little attenuation as possible, but at the same time, whatever your customer needs. What is interesting is the relationship to the temperature, because if you start increasing the temperature, you don't cool it down properly, the bit error rate gets better. So is this our message? Shall we heat up our transceivers? No, basically it's a control circuit that is targeting the eye diagram. It is, how can I explain? Actually, what you want to achieve is to have a perfect eye. That is what you usually measure in an oscilloscope when you're measuring all the lines. And if you give it the right time window, you get to see an eye, because it jumps up, it jumps down the signal, and it forms an eye. It's never perfect. Perfect would be a rectangle, but it looks more like an eye. And this eye gets messy when you start increasing the temperature. So what happens with the laser is through a control circuit, it changes the power because the laser also have to be at a certain temperature. It's not the temperature of the transceiver itself, it's inside the transceiver, a specific temperature you have to keep up in order to have a good signal. So that is what basically happens here, but as you see, if the temperature continues increasing, it gets worse. And with a 2 meter, you have very strange jumps. So yeah, temperature is a little bit annoying on that side. Getting back to the bit error rate, so this relationship seems simple. You also have to consider a little bit of statistical noise, Gaussian noise. It is called, usually you take a sample of 100 errors. Why do you do that? Because the idea of gating time is, you might read this in the specification of transceivers, is that you take a sample and you just assume that, well, there's a certain probability that up to 100 errors I receive if I wait, I don't know, 16 minutes, for example. And considering a bit error rate, which is a good value, 10 to minus 12, it takes 16 minutes you have to wait, in which you can consider, yeah, there were mistakes. Why are we doing this? Why are we assuming that? Because if you measure your first error, So your error could be erroneous. It could be a fake measurement. It wasn't an error after all. So that is why you better take a sample of 100 so that you can be sure that something is going wrong here, right? So that's a little bit the idea of gating time and bit error rate in its relation. Now, one that was interesting, yet again, thanks to the Cisco guys, we used an old heatsink fan. So this was very helpful in order to cool down these transceivers because our Flexbox, I have one here, do not cool down. There's a certain reason we want to keep this compact, so we have to go this measurement. And yeah, we took this from an old Cisco 800, and what you see below this heatsink is a coherent transceiver, a 400ZR this time. And I will show you more curves, but no worry, even though this transceiver is more complex in its inside because, 16 QAM coherent signal, the diagram will be much simpler. But first of all, we have a friend who does a little bit of scrap management. He takes old switches, old routers, everything that others would throw away. He collects it, he recovers all the copper, and from him, basically, we got the heatsink. So if you're interested in dumping anything and you want to have it recycled before you throw it away, feel free to approach our CTO because they are best friends. Anyways, getting back to the coherent, I think this looks better for one advantage, and that is what speaks a lot of if we can remove some correlation. I don't use attenuators here because it's not required. Why? Because you can easily connect a 2-meter cable, but you can also connect up to a 60-kilometer cable. We have a different specification for the range, so we don't see any red out of Ethernet specification because a coherent is more tolerable to higher bit error rate. So if you start measuring it on coherent, you will see a higher error rate, but that is okay because it is better at recovering the signal. So you don't have to care that much. And the good thing is the temperature also doesn't matter anymore. Not so much. I mean, it's a little bit, but really what changes a bit error rate is your fiber length, your cable. So the attenuation of the cable itself. Yeah, we also tested this without cooling. If we started, the thing with a bit error rate is in the background, there's a counter running. So you start with a higher value if you don't cool it down. It was a very short test. After that, we cut off the current, and yeah, that is what we measured. Now, a more interesting experiment, I brought a transceiver here that we got up to 120 degrees. It is that one. I'm going to connect it, and we will see if it still works. Yeah, but don't do this at home, so do it in a protected or more or less protected environment. I call this a transceiver barbecue. You can search this for YouTube. There's a whole story about it. And yeah, in order to properly see the transceiver, you can see the yellow ledge, but not everything else. The photo's not that good. I used the heat gun, not these heat guns that is for the hair. It's a special one that can go up to 600 degrees. So be careful with that experiment. And yeah, I tried it out with 2 meters and wanted to see how long it survives if we make it too hot. Usually when you connect your transceivers to your network gear, you can read out high warning, high alarm. That is pretty usual on managed switches. And we wanted to find out how realistic are these margins? How much can you go beyond those? Usually, what we do in our software is have it locked at 65 degrees. We consider that a lot. So I started heating up the transceiver without the heat gun, wanted to see what happens with the software. I'm fine, 65, it quits. So I removed this safety mechanism, let it run until 100 degrees, but we wanted to see if we can go up to 100 degrees. So after I found out that the signal got lost, I retried, that is the green curve, if I can go up to 120. Yeah, but at around 80 degrees, the signal is lost, basically. But on this another try, it still was responding. So then with the fourth try, I wanted to see if the transceiver still works and how the bit error rate will be. And I was kind of surprised that I hit the right spots with the temperatures. It went up a little bit, but it recovered itself. So The transceiver survived the 120 degrees. But yeah, it's something you should not do usually. But just to get a feeling what happens if you go beyond high alarm and high warning. Yeah, that curve. I already explained it a bit. Bit error rate is a counter, though you can have this effect that it doesn't recover entirely the bit error rate. That is because you have a counter. You would have to reset the counter. So don't be surprised if you remove a cooling device and put it back, that it doesn't go down to the where you had at start. Having said that, you already saw this image. I'm going to show you a live demo, a small one, so you can see how this works, and we'll explain a little bit more about, we were talking about two values, which was bit error rates the whole time, but also the OSNR, you remember, with the noise, if I speak out loud or not, and if you can hear me. So we are going to measure that one and bit error rate. Just let me start this guy here. Come on. Don't fail on me. If it doesn't work this time, you know, it survived 120 degrees. Yeah. No worries, it takes a little bit of time, but it was detected, as you can see here below. Yeah, it takes a bit of time to boot, but what you are seeing here is, and one of the more modern switches or network in general can do is, we are starting the PRBS, the diagnostics capability of the transceiver. And I think that has a big advantage because is it the fiber, is it the switch or your network gear, whatever, or is it the transceiver where the problem is if you have too high latency times, or if your bandwidth is going down or whatever reason. Well, here's just the Flexbox with the transceiver testing it, and as you can see, it still works. 2-meter fiber, 10 to -12. It's still doing its job. It goes a little bit up. The temperature goes up. That is normal. It's also related to the counter, but as you can see here, we have temperature, reception power I put here. I could show more diagrams, but I think with 4 it is more than enough. It's really the most interesting part we are seeing here. That's the resolution. We can also get more frame per second if I turn off the optical SNR, so it gets gray and it's more fluid, but it is because OSNR and bit error rate share the same page in memory. So you have to be telling the transceiver, please show me that value, please show me this value. It's diagnostic selector, it is called. So obviously it's faster because I'm not switching the diagnostic selector anymore, but if I disable this again, it starts switching, and yeah, it's more work for the transceiver basically. Yeah, and that's it basically with the practical part. Let's get back to a couple of slides, because let me be honest, we were a little bit dissatisfied, so we tried another transceiver, put it up to 250 degrees, and wanted to see if we get it destroyed, because I mean this guy still continues working. So, but we took a different one. By the way, I also have it here, but I will not show in the presentation if it still works. I put another label on it. It melted down the label, so yeah. This really went far beyond that. I added a weird limit. This is an unofficial limit, because beyond 128 degrees, it starts reporting negative value. If some of you already have developed in C language, for example, and heard of signed char or unsigned char and the difference, that's the reason of it, because the first byte, it needs to be flipped in reality if you want to measure this temperature correctly. Beyond 180 degrees, I mean, yeah, you're really dealing with very strange effects. And yeah, the signal got lost. It also recovered, but when I rebooted this transceiver, the reception was way worse. So basically, yeah, the photodiode does not work on that one anymore. So yeah, once again, the message, don't try this at home. And with that, I'm almost finished. Here are some takeaways. So direct detection transceiver is a non-coherent one, we can call it. It still depends on temperature a little bit. Bit error rate will always be a rolling average temperature, which means what you actually read is based on a counter that is divided by itself, and it always takes the last value, divides by it. That's the reason why it behaves like it behaves, what I showed in the previous curves. So difference between high alarm and high warning is not so much. So keep an eye on these values. If they're shown on the switch, try to be below the warning. Coherent transceiver benefit from more properties, as we have learned even in the previous presentation. With more features and more signal recovery, the temperature does not affect the bit error rate that much. Yeah, and that's it basically. And by the way, this presentation wouldn't be complete without any AI. So we used the AI to generate some odd pictures, and not sure if it looks for you like a transceiver. I found it interesting, so why not? Anyway, that's that, and thank you very much for your attention.
All right. Are there any questions? We have times for questions since nobody said slow down.
Yeah, I'm surprised actually.
All right. Then I think we can take our break. It will going to be a bit longer break, but then we'll also have a bit longer session afterwards. And then yes, we're going to wrap at 5 with a quiz after this next section. Thank you very much. See you.